Hello, my name is Phil Simcoe, and I'm the product manager for Amazon Quantum Ledger Database, or Amazon QLDB as we call it. I'm joined here today by Mike Labib, QLDB's principal solutions architect. Today I'll be discussing some of the background around why we built QLDB, what value it brings, and the use cases for a ledger database. After this presentation, Mike will give a demo of QLDB. After Mike's demo, we'll leave time for Q&A. Let's start by looking at a problem our customers face and the need for a ledger database. Our customers have what we call system of record applications or data. These are applications that require history, data completeness, and data integrity. A ledger provides these qualities out of the box, but they come in two flavors. The first is centralized. When talking about centralized use cases, this ledger serves as a transparent, immutable, and verifiable record for a company's application. And it does not have the notion of decentralized trust or data sharing across nodes. A good example of a centralized use case is a company that has a supply chain where it wants to have transparency and real-time information of every change or action taken throughout the chain. This makes auditing, tracking, and dissecting issues much easier. Today, building such systems is complex and requires multiple technologies to track history, such as audit tables and audit logs, and there is no built-in verifiability. Similarly, there are many other examples in healthcare, HR and payroll, government agencies like the DMV, and so on, that need a centralized ledger for maintaining their data lineage and transactions. The second customer need is of companies who want peers or consortiums to work together and execute applications that share data with one another without a trusted central authority. Let's take an example of trade finance. Trading goods across international borders requires many organizations to work with one another, such as importers, exporters, multiple banks, shipping and insurance companies, and customs departments. Trade finance consortiums want to transact with decentralized trust, allowing multiple parties to agree on a protocol for recording transactions and distribute a copy of the transaction ledger to each participant for independent verification. No single participant owns the application, and thus the business application becomes highly efficient. Similarly, there are many other examples for mortgage lenders, supply chain businesses, and retailers. At the end of the day, it depends on each customer's unique use case and whether they need a centralized or decentralized ledger. As many of you know, ledgers are not a new concept. For at least the past 5,500 years, record keeping has been a central theme to civilizations around the world, and they have had to deal with the same kinds of problems that we do today. Traditionally, ledgers have been a book or other collection of financial accounts of a particular type. However, we see ledgers used not only in financial use cases, but any situation that requires any type of system of record. Here are a few examples: banking and finance, manufacturing, or ownership of an asset. And that brings us to Amazon QLDB, a fully managed ledger database that provides an immutable and verifiable transaction log owned by a central trusted authority. Applications are no longer built as one huge monolithic application, but developed in smaller pieces leveraging microservices or serverless architectures that use a variety of databases that are purpose-built to meet their application's specific needs. Here we see QLDB as part of our purpose-built database family, as our ledger solution. QLDB provides the complete and verifiable history of all changes to your application data. Amazon QLDB is built with tried and tested technology used inside Amazon for years to solve the problem of building reliable system of record applications at scale. QLDB gives you immutability. The database maintains a sequenced record of all changes to your data written to an append-only journal, allowing companies to query and analyze the full history of their data. Data in QLDB is cryptographically verifiable. The service uses a cryptographic hash function, SHA-256, to generate a secure output file of your data's change history, known as a digest. And the digest acts as a proof of your data's history, allowing you to look back and validate the integrity of your data changes. QLDB is a serverless database and scales with the application. Unlike common blockchain frameworks, which require consensus, QLDB performs at low latency and higher throughput, not requiring companies to trade performance for verifiability. Finally, by leveraging familiar SQL APIs and a flexible open source document data model, Amazon Ion, QLDB is easy to use. Companies can reduce risk by ensuring the safeguarding of critical system of record applications where data loss could be expensive. Also, QLDB provides improved data tracking, which helps parties that have access to the system to quickly and accurately track their data's entire lineage, improving efficiency in identifying the source of issues. Examples of this can include manufacturing defects or maintaining a supply network data hygiene. Providing auditability helps reduce downtime caused due to audit and compliance issues or inspections, saving hundreds of productivity hours. Having immutability and verifiability as key features of QLDB allows companies to leverage the benefits without having to build them in a traditional way, which is time-consuming, complex, and expensive. This is a high-level example of how QLDB works. Like any other database, your application will write data into QLDB. When data is written to your ledger, it is first committed to the journal. The journal provides immutability and verifiability by storing a log of each transaction in a sequenced way using cryptographic techniques. It is then written to the current state and index tables, which, as the name suggests, stores the current and historical values of all your data. Here we provide some additional architectural context. We can see a ledger with data from a DMV, so in this case, tracking vehicle history. First, your application connects to the ledger to begin executing transactions. The data is first written to the journal. Since the journal is append only, it keeps a record of all changes, including updates and deletes. These transactions are sequenced and hash chained to provide history and data integrity guarantees. This journal is also what determines the state of your tables. Once the data is written into the journal, it is materialized into your tables. Leveraging these tables allows for faster and more efficient queries. In the example, we see that the current table shows who the owner of a specific car is, while the history table shows us the history of the same car, noting what version of the data each entry represents. When the application reads data, it accesses the tables and indexes stored in your indexed storage. This table maps basic concepts between a typical relational database and QLDB. In QLDB, your ledger is the database. Your ledger has tables and indexes, much like an RDBMS, but QLDB's data model is document-based. So a row is equivalent to a document, and a column would map to a document attribute. Lastly, we provide a variant of SQL to make accessing your document data simple. And with QLDB, the journal is your always-on immutable audit log. In these next few slides, we show the details of how QLDB works by revisiting the DMV application example. On the left side, you see an interaction take place through the DMV's application. On the right side, you see a visual depiction of QLDB's journal and index storage and how it behaves when application data comes in. In the first step, Tracy buys a car, and the immutable journal stores an entry of the insert. The tables in the index storage will also show Tracy's record as owner of the vehicle, and the history table will show an index list of all entries in the journal, which for now is just the insert. In the second step, Tracy sells her car to Ronnie. Now notice that the immutable journal appends the record, not overriding the previous record. That current state table shows the change made and that Ronnie is now the owner. When we take a look at the indexed history, though, we see the full lineage of the vehicle's owners. Finally, in the third step, let's say Ronnie gets in an accident and totals the vehicle. Again, the immutable journal does not delete Ronnie's record, but instead appends a delete record as a new entry. The car no longer exists, so the current table is empty, while the history still shows the full lineage of the data. Now look at verifiability and how QLDB uses cryptographic techniques to ensure your data's integrity. Using the same DMV example, we see each of the 3 transactions that took place in the last slide. Each transaction, when written to the database, is hashed using the SHA-256 cryptographic algorithm. QLDB chains each transaction to the previous one by taking the hash of the transaction before it, adding the new transaction's information, and hashing that together to provide the next link in the chain. QLDB can then use these hashes to verify that the data in the journal has not been tampered with, providing data integrity guarantees. In comparison, in an audit log set up with a traditional database, a super user with the right privileges could potentially modify historical data without leaving a trace behind. Amazon QLDB is serverless and automatically scales to meet the demands of your application without the need to provision capacity or configure read and write limits. It is also highly available and durable, replicating across multiple availability zones and providing multiple copies in each. In comparison to blockchain frameworks, QLDB provides better performance and scale, executing 2 to 3 times as many transactions. This is because blockchain frameworks are decentralized and require peer nodes to validate a transaction before it can be stored in the ledger, impacting their performance. Executing a transaction in QLDB is as simple as any AWS database. QLDB is easy to get started with and use. It leverages Amazon Ion as our document model and SQL-compatible APIs. On the left side, we see an Amazon Ion document. Amazon Ion is an open-source document format and a superset of JSON, meaning that any valid JSON document is also a valid Ion document. It is based on an abstract data model that lets you store both structured and unstructured data. This provides developers interoperability between text and binary, more data, number, and null types, and other features. On the right side, we see some example QLDB SQL syntax. QLDB SQL supports a subset of SQL that has been extended to support Amazon Ion documents. You can insert, update, and select with familiar SQL operators. When querying flat documents, the syntax is the same as querying a relational database table. QLDB supports full ACID transactions and provides the highest level of isolation, full serializable isolation. There's no risk that you'll see phantom reads, write skew, dirty reads, or other issues. To recap the key features, QLDB is a ledger database utilizing components of blockchain technologies to provide a complete verifiable history of all application data changes. It is built with tried and tested technology used inside Amazon for years to build reliable system of record applications at scale. QLDB gives you immutability. All data changes are written to an append-only journal and cannot be changed or deleted. Data in QLDB is cryptographically verifiable. Transactions are hash chained together to verify that the data in the journal has not been tampered with. In comparison, in an audit log set up with a traditional database, a super user with the right privileges could potentially modify historical data without leaving a trace behind. QLDB is serverless and automatically scales to meet the demands of your application while performing at low latency, so you don't need to trade performance for verifiability. By leveraging Amazon Ion and SQL-compatible APIs, QLDB is flexible and easy to use. With ACID transactions, QLDB supports full serializable isolation. And finally, QLDB is a journal-first database, providing a full, immutable history of any data written to your ledger. In this slide, we talk about the problems customers may face while implementing a centralized ledger or building a system of record application using traditional database technology or distributed/decentralized ledger technology. Many customers may try to set up a ledger using a relational database. However, relational databases aren't built to be immutable or to be cryptographically verifiable. So customers try to recreate this functionality with audit trails and audit tables. But it's hard, complicated, and expensive to build and maintain. Also, there's no way to verify that the database engineer who has full access to the system has not accidentally altered the data. On the other hand, some customers are trying to use blockchain frameworks to solve the centralized use case. But blockchain networks are meant for a different purpose, specifically decentralized use cases where there are at least two parties or peers. So, blockchain frameworks need at least two sets of peer nodes to be set up before saving transactional data to the ledger. This setup can cause unnecessary complexity for customers who have a centralized application. I'll finish by briefly recapping the range of industries and use cases for QLDB. Banking and finance have various use cases involving the tracking of transactional history. E-commerce and retail more generally maintain inventory or track supplies. And we've spoken previously about transport and logistics, where understanding where goods have been and when they were there are critical. We also see our DMV example under government, which is the classic use case for asset tracking, a common ledger use case. The use cases are quite broad, and QLDB can be applied anywhere where there is system of record type of applications that need a centralized, performant, and verifiable ledger. And now, Mike Labib, our Principal Solutions Architect, will give a demo of Amazon QLDB.
Thanks, Phil. So here's the QLDB Service Console page. And if you look over to your left-hand side, there's a few different options, including viewing your ledgers, and there's a query editor. There's some links that we'll kind of walk through a little later that allow you to do verification and some sample data with building an application. What we're going to do first here is we're going to create a ledger. I'm going to give this ledger a name. I'll call it DMV because the content of the data that we're going to store is DMV data. There's some optional tags for this demo I'm going to skip. And so while this is creating, essentially what's happening here is we're building out that journal for you in the ledger for you, right? And that's happening across multiple availability zones within a region. There's multiple copies within each availability zone, so this is highly available and durable. And this generally takes a few seconds, maybe 10, 15 seconds to run. So very shortly here, this is going to say success. And it does. So at this point, what we're going to do is we're going to click Query Editor. As soon as you do that, you select the ledger that you want to run your queries on. And for this demo, I'm going to go ahead and create some tables. So we'll do 4 tables. So I'm going to do vehicle registration would be the first table. That looks correct. After that, we're going to create a table that's going to store vehicle information. Simply just going to call it vehicle. And we have a table for persons. And we'll also create a table for driver's license. All right. So now that we created our tables, we can actually even create some indices at this point if we knew what our data looks like. But instead of that, what I'm going to do first is I'm going to load some data. And I'll go ahead and start by loading driver's license data. And we'll clear that first query. We'll load that, and we'll go ahead and just take a quick peek at what's in there. There's a driver's license, license type, some validation dates, and there's a person ID here that's missing, and we might do something about that later. So we'll go ahead and do run. We'll go ahead and do the same thing for a different table. We'll grab the person data, run that as well. Okay, run that. Then we'll grab some vehicle registration data. And one thing to notice is that there's a nested document here called owners. And owners, two different attributes, a primary owner, a secondary owner, and then there's missing values here that we're going to make changes to a little later. So you can see here there's a value for person ID missing, and then there's an element for person ID as well as its value missing for the secondary owners. I'm going to go ahead and commit that as well. So that is committed. And then we'll finally grab our last data set, which is for vehicle. And we'll store that as well. And just go ahead and run it. So now that we stored data, let's just kind of get an idea and a feel for how that data looks like. So I'm simply going to just write a query against maybe the vehicle table. Oops, let's just make sure we get that right. There we go. As v where v.vin equals, and I've stored a VIN number that I'm going to be using throughout this presentation. So we'll just copy and paste that one here. And let's go ahead and run that. And you get back what you expect to get, right? So if you go back into that vehicle table, these were my attributes. These were the values that I stored, and that would match what the user table is giving me back, right? This is the user data that I persisted in the journal. All right, so let's, while we're at it, let's go ahead and query maybe another table. So I'll go ahead and modify this query, make it the vehicle registrations query. And if you recall, there was also a VIN value that was stored in the vehicle registration. Let me go ahead and run that. And in the vehicle registration, we have some license plate information, where that particular vehicle was registered, as well as this nested document that we talked about earlier, where primary owner is missing some values, as well as secondary owners. So just make a mental note, make some changes there a little later. So while we're at it, we talked about VIN being in a vehicle table as well as vehicle registrations. So one thing that's pretty neat about QLDB is it supports joins as well. So let's go ahead and make a change here and see how that might look like. So we'll do that. And we'll actually just call this one R. We'll filter on registrations, and we'll just add a v.vin equals r.vin. That should do the trick. So we'll go ahead and just run that. And so what that just did is it gave me the additional values or attributes from the other document, right? This might be useful if I want to see details about the vehicle as well as the vehicle registration information. But the output of this, obviously, we haven't made a change to owners, so that data is still not there. So we'll go ahead and make a change to that perhaps now. Now, before I make that change, if I take a quick look at, say I want to store a person record in this person document, in this owner's value, or this person ID value, I want to decide what type of data to store, right? So let's just take a quick peek at our persons table. And if you notice, once that comes back, is that I don't actually have an ID that I persisted, right, within my user data, right? So what's neat about QLDB is that we're actually generating a unique ID for you for each particular record. And the way that you get at that ID is you query a committed view that we also have with the data. So let's go ahead and select the specific ID for a particular user, or document ID for a particular user. And the way that we do that is we query that committed view. So we'll do committed underscore person. We'll give this an alias as P. And then we'll apply a filter, which I actually have handy here. So I'm going to grab the document for a particular user, and I'll explain where this data comes in here. So we'll go ahead and run that query. And so what you get back is this is the committed view of that data. So the first view that I showed you was basically the user view. It's basically the values that the attributes of that document that you persisted. In this committed view, you see what was actually being stored and committed in the journal, right? And so this includes the block address of your data, the particular hash value for that document, the user data that you stored, which has all the elements and values that you stored, or the attributes and values that you stored. And then there's this metadata, which is also being stored with your transaction, and that includes the unique ID for that document. It also has really interesting information here, which is the version of that document, the transaction time, and the transaction ID. And we'll use some of those other attributes a little later in this demo. So I'm going to make a little note of that ID for that user, because that's what I'm going to be storing as a ID in my vehicle registration. So let's go ahead and again remind ourselves how that vehicle registrations table looks like for that particular record that we want to modify. We'll grab the VIN again that we're using, right? So we're just selecting everything from that particular table and filtering on that VIN. Let's go ahead and run that query. And so what we're going to make a change to here is this: we're going to apply a person ID or a value in that attribute. So let's make an update to this table. So the first thing that we're going to do is use the update command, right? So update vehicle registration, which is the table that we're making a change to. We're going to set a value, so it's the owners primary owner dot person ID equals, and then we're going to use that value that we just retrieved from the metadata from the committed view, and that metadata ID again is that doc ID. And if we just look again here, we're drilling into owners, primary owner, and then person ID, and then we're setting that value that's currently empty to a particular value, and then we're filtering on that same VIN that we've been using throughout this demo. So let's go ahead and run this query. Great. So that just worked. I'm going to just make sure that that actually took effect. So we'll do select star from vehicle registrations. We'll remove this set statement. All right. So at this point, I'm going to go ahead and query that vehicle registrations and just make sure that the value is actually there. So we just queried that, and you can see that that value for person ID was now just persisted as we expected. All right. So let's make another change. How about we add a secondary owner? Now, if you notice with secondary owners, it's actually missing not just the value, but an element, which is the person ID, right? It's an attribute called person ID that we want to add. So the first thing that we want to do is we want to grab that ID for another user. So I'm going to go ahead and select. Because I know what I'm going after, I'm going to just go ahead and type metadata.id from, let's go, QL committed person as P, where p.data.first name, actually I stored that as well, so let's save my typing. We'll go ahead and grab this. Okay. Delete that extra character. So this is going to give me the ID for Raul Lewis. Okay. Let's go ahead and run that. I'm just interested with that document ID because that's what I'm going to use to store in my secondary owner field for the vehicle registrations. So let's go back and query vehicle registrations. So we do select star from vehicle registration as v, where v.then equals. We'll use that then again that we love. Store that there. Just kind of take a quick reminder of what that record, that document looks like. And there's an empty secondary, and then we'll make our change, but this time we're going to use a different type of command. We're going to use a from command, and froms basically allow us to modify, remove, and insert elements where needed, right? So we'll do from vehicle registration as v, where then equals that then, we'll filter there, and then we'll do an insert into v dot owners, secondary owners. We'll stop there because what we're actually inserting is also the attribute, right? So curly brace, we'll call it person ID, and then we'll apply the value, and the value is the document ID that I just grabbed. We'll just use that document ID, store that, and go ahead and run that. Let's see, let's make sure v owners dot secondary owners, and we're adding a person ID attribute with its value. And let's go ahead and run. So that's a success, right? So if that was successful, then we should see the change, right? So let's go ahead and query that again. And remove some of this unneeded statements. Go ahead and run that. What we have now is within this nested owners attribute or document, we have a value for person ID, and then we have this new element, person ID for secondary owners. So that is now the way that we like it. But if you're keeping track and you're following the idea with what's taking place with the journal, there is some history that's taking place, right? So there's some revisions that we've accumulated as we've kind of made these updates. And so we'll take a look at that next. So the first thing that we want to do when we query history is the history itself is a function that requires a table name, a start timestamp, and then an end timestamp. And that's the timestamps are essentially in UTC format. So what I want to do is before I actually call that history function, I'm going to go after the committed view again. And I'll explain why. Because in the committed view, if you remember, I have that transaction time that I want to use in reference when I actually call that function. So let's go ahead and query from QL committed vehicle registration. So what we're doing is we're going after now the vehicle registrations because we want to see the history of revisions for that particular VIN that we've been making so many changes to. The other thing that I want to do is add a filter. So I'm just getting back what I'm looking for. So we'll do data. VIN data again is the user data. And I'll use the VIN value that I've been using throughout. So we'll go ahead and do that. And so let's take a quick peek here. So I'm looking at the committed view. I'm grabbing the transaction time from the metadata. I'm also grabbing the ID, again, which we said was a document ID. And I'm going to use both of those in my history query that I'm going to show you in a bit. And this is going after the committed view for the vehicle registrations. And again, we're filtering on that VIN. So let's go ahead and run that. All right, so we got back a transaction time for the last update, which really isn't an update. It's just a new document that was stored, a new revision for that particular document. And then we have the ID, which is the document ID. So I'm going to go ahead and store that information here. Just make a note of it. And we will use that next in our history function. So we're going to go after history. So we do select star from history. Again, we said history was a function. So the first parameter is the table name. So we're going to do table name, do a comma, and then we're going to use a tick. This tick is really is used to define a Amazon Ion literal. And so this particular case, it's a timestamp, and we're basically saying start from 2000 is my starting point. And in my endpoint, I'm going to go ahead and use that timestamp that was just recorded in the committed view for that last document that was persisted. And I'm using that because I know that there was a document, that was the last revision that took place. Now, if I just executed that, I'd get everything within that duration of time. So what I'm going to do instead is I will filter. Let's do as H, and we'll do where H dot metadata dot ID, and we'll go after that document ID that we just grabbed as well. So essentially, what we're saying is we want to see the history, the revision history for a particular document within a duration of time. And let's see how that looks like. Let's make sure our syntax looks correct. It looks correct to me. Let me go ahead and run that. And we got back 3 documents. Now, if you remember, the 3 changes that took place was the first one was the initial record that I loaded, an initial document that I loaded that was missing some values. The second one, we made a change by adding a person ID, which was really the document ID that came out of the person's table. And the second revision for the same document included a new element, which was a person ID and a value for that person ID for that third person. And if we examine the metadata very quickly, we can see that we're operating on the same ID for all of them. We have the 3 different revisions. We started at revision 0. We're currently at revision 2. Revision 2 is what's being reflected now in that committed view, which is showing me the latest view of my data. And what's also captured here is the timestamps for each one of these documents that took place. And if I scroll all the way back to the left, I have the block address, which is really telling me where in the journal it's located, as well as the sequence of that location. And there's also an individual hash for each one of these documents that were stored. All right, so we retrieved back some data. We saw the revision history. We executed some queries. We made some updates. Now let's maybe do some verification. Like, let's say we want to prove that a particular value is in fact accurate or belongs in the journal, right? A particular document is valid. So the first thing that we want to do, if we go back to that left-hand side, is we want to click on verification. And the first step really is grabbing the digest for the journal. And the digest essentially is that SHA-256 hash that is provided in the ledger. And we'll go ahead and click that. We'll select which ledger we want the digest for. We'll click Get Digest. And then I'm going to save this and just have it handy, really just opening it and just keeping it handy with me. And just a couple things that get returned back. The digest value, again, this is that SHA-256 value. And then there's that digest tip address, which is the latest block location in the journal for that digest, along with additional metadata like the name of the ledger and the date, etc. Right? So we'll keep that handy there. We'll go back to verification. Actually, we'll go back to query editor. All right, so the next thing that I want to do is I want to grab a document that essentially we want to verify. And so what I'm going to do is go after the committed view again for the last version of that document that we've been changing. So let me go ahead and query that. So we'll go select star from QL. Oops. Registration as v, where v dot data dot then equals, and we'll grab that then that we've been using throughout again, and we will run that query. Let's make sure our syntax is correct. Okay. And what we're going to grab here is two things. We're going to grab the block address because we're validating not only that document belongs in the journal, but also the address of it, right? Where its location in the journal is actually correct as well. So we'll grab also the ID for that document. Store that below that. All right, and now we basically have what we need, right? We have the digest information, and we have a document that we want to validate against that digest. So we'll go against the verification screen, and we'll select it's already pre-selected in my case, the DMV ledger. We'll pass in the block address for that document that we're validating, as well as the ID. And then we're going to take the digest information as well. So we'll grab that SHA-256 hash for the digest, as well as the location of the digest. Okay. Looks like there's a special character here that I'm going to remove. Okay. And I think we essentially have what we need. So we're basically saying, I want to validate the document with the digest that I just provided it. We're going to click verify. What we see here is we have a successful verification. The proof was completed, so the digest was essentially recalculated with the inputs that we provided it. You can see the Merkle tree proofs that took place, essentially just recomputing that digest based on the starting point of that document. And if we want to investigate what was in that the block, we can also see the SQL statement that created that document. We also have the document entry on our right-hand side that has the details that are recorded in the journal. All right, so finally, this concludes the demo for today. The one other thing that I could have showed you guys is you can also export the journal as well. But for a later time, we'll be more than happy to cover that with you. Thank you again for your time. I'm handing it over to Phil. Thanks again.
Thanks for the excellent demo, Mike. Thank you for taking the time to join this webinar, and we're excited to answer your questions about Amazon QLDB. If you'd like to join the preview, please register for the preview on the AWS website under QLDB. Thank you.